Okay, so let's continue and wrap up Chapter 9. And this is the last section where we're going to talk about population variances. So remember, we did do an investigation for one population variance at the end of Chapter 8. Now we're going to look at two variances. And remember that talking about a hypothesis test or a confidence interval for a variance, it's very different fundamentally than the last two examples we did of means and proportions. One of the first things we run into as a snag is that the variance itself, it can't be negative. So we're automatically going to lose things like symmetry. Remember, with the t-test and the z-test, the underlying distribution is symmetric. This is not true for the variance and therefore the distribution of the variance. So remember that in the last couple of chapters, we had a variable, I don't know if we called it x, but we had nu s squared over sigma squared, this scaled version of the variance, and that led us to what was called a chi-squared distribution. And nu was the one parameter, the degrees of freedom in that case, just like it is for the t-test. And that was used as chi-squared distribution to do probability tests for the variance. We were able to construct confidence intervals, and we actually skipped over hypothesis testing, but now we can go to hypothesis testing for two variances. And so the first thing we'll have to do is introduce a second variance, and when we do so, we're going to form a ratio of the two. So we're going to think about taking x1, where x1 is this quantity with s1 and sigma 1, and then we'll do the same thing with x2 and divide them and see what happens. Okay, we'll get a different distribution, and if you haven't guessed yet, we have a name for it. It's called the F distribution, okay, based on the variable, and it'll have two different parameters, nu1 and nu2, the degrees of freedom for both of our samples, x1 and x2. I'm sorry, x and y rather. And so the numerator degrees of freedom is what goes in the numerator of our F distribution. We'll usually think of that as x sample, and then S2 corresponds to the y sample. That's the denominator degrees of freedom. So when we divide this particular quantity, right, you plug in the expression from the last slide for x over nu, and x1 over nu1, x2 over nu2. You can rewrite that in terms of the variances, and it's the ratio of the sample variance over the true variance. Remember, the true variance is something we don't know, but because we can compute sample variances, we can now form both a confidence interval or a hypothesis test for this particular F quantity. Right? So let's see what that looks like. Here's a picture of the F curve, okay? And as you can see, it's very asymmetric. It's kind of like the chi-squared distribution, but it actually has some nice properties that we'll see in just a minute. You can construct the critical values, which give you a certain proportion of area in the tail, and that will have all the usual implications for our tests that we proceed with. So this is what our critical value will be denoted as. Right? We have alpha, which is the proportion in the tail, and then we have these two parameters for the numerator and denominator degrees of freedom. This is the nice property, though. If I compute certain proportion alpha in the tail with nu1 and nu2, if I take the reciprocal of that f and I think of the lower tail as having alpha, in other words 1 minus alpha in the upper tail, then this relationship will hold. And this is nice if you're using something like a table to compute F values, because now, unlike the chi-squared distribution where we had to compute lower and upper tails separately, we can just think about reversing the role of nu1 and nu2, and you can compute all the critical values with just an upper tail. Okay? We'll see how that works in just a moment, but actually we're mostly concerned in this case with getting the software to do F tests for us. But it can be done with the table as well. So let's suppose that we've already chosen a significance level alpha, or maybe a confidence level if we're thinking of a confidence interval, right? This is the type of statement that we begin with. Remember, we've done this several times now. We started off by thinking of confidence intervals for the sample mean in exactly this way. We used to have z there, and z was x minus mu bar over, x bar minus mu rather over sigma. Now we have the variances that go there, and these F values, right, they're not going to be the same, but they are somewhat related. And we still know that the left tail and the right tail have a total of alpha area, so therefore this probability is going to be 1 minus alpha when we compute it. Now, if we solve for the quantities we don't know, in terms of the random quantities that we will know, the quantity of interest becomes sigma 1 squared over sigma 2 squared. So we first solve for that, and when you do so, you get this sort of a structure for the confidence interval. So we'll need two different f values, and once we compute those, we divide the ratio of the variances by those. Okay? If we want to do something with hypothesis testing, we read this in a slightly different way. Let's suppose for my hypothesis, I'm thinking that the variances are equal. So I plug in that the variances are equal here, and that makes sigma 1 equal to sigma 2. Now S1 will in general not be equal to S2, but I can decide whether or not my sample variances bear out my hypothesis, and in this case I get at the very least a rejection region criterion. Okay, and that means that if S1 squared over S2 squared that I've computed is between these two values, then I do not reject the null hypothesis. But if S squared over S2 squared is either bigger than this value or smaller than that value, then the corresponding p-value is small, and I would reject the null hypothesis. And therefore I would reject the notion that the variances are equal. So these are the two things we can do with a ratio of variances. Okay? Now, p-values require some care because if you think about how this might be different than the z-test and the t-test, it's the fact that this value here is not simply the negative of this value. We've lost the symmetry, and that's again due to the fact that this quantity is never negative. Okay? So, we've got our picture here, and let's think about what sort of what sort of hypothesis testing we would have. Okay? If the variances are not equal, there's our usual three cases, and the first two are not too bad, but as indicated on the last slide, some care is needed, especially when we're thinking of the two-sided test. So what's generally done is we'll take the minimum of the two outcomes of thinking of the upper and the lower tail. Okay, and this is again a consequence of the fact that we don't have a nice symmetry property that we can apply. I don't know that the tail on one side is simply double the tail on the other side. So we have to use this minimum expression and double that instead. And this is an approximation for the actual p-value. Okay. Which is again why it's more beneficial to just use hypothesis tests that are built in Minitab or Excel if you download the analysis tool pack. So let's look at an example. Here, serum ferritin is used in diagnosing iron deficiency. You can see the root word here. Is it Greek or Latin? I forget. Ferrous, iron, and so forth. But anyway, we're looking for iron deficiency in this example. And usually elderly people, they have iron deficiencies. So we're going to compare the amount of iron in men that are elderly and also young men, and just see, is there a substantial difference in the variability of the two? Okay, so if elder gentlemen tend to lose their iron content, then the variability would also shrink as they get older. So that's what we're looking to test here in this case. The sample standard deviations, they tend to bear this out already. As you can see, 52, much smaller than 84 for the young men with their iron levels. Okay, but now let's actually do a test. Are the variances equal? Is it possible that they're equal? So we'll form our hypothesis test, and if it's wrong, then we're definitely interested in the less than category, right? If S1 is less than S2, then if the null hypothesis is rejected, I'm looking for this alternative hypothesis. Okay, so we'll test that with a 1% significance level. And we can run this in Minitab. Let's go ahead and do this example, just so you can see it. Okay, I'm going to go to let's see here. Okay, not one variance, but two variances. Okay, it's not labeled as the F test, unfortunately, but that is what we're looking for. Okay, and we don't have anything in the column. It's not. If we did, it would compute the sample variances for us, but we're instead going to give Minitab directly the summary data, that's been provided in the slide. So let's see. For my first sample, what was the sample size? I tend to overlook that. Oh, I guess the information is here too. Let's see, 28 is the first sample size. And the standard deviation is 51.2. Sorry, 52.6. And 26. And we had 84.2. Okay. And what else do we have to check? We have to make sure that our hypothesis statement matches what was asked for. Okay, they asked for a 1% significance. So let's go there. And we're not forming the ratio of standard deviations. We're thinking of the variance. We could take the square root of the results if we're interested in specific values. And we're thinking that sigma 1 squared is less than sigma 2 squared for the alternative hypothesis. Hypothesized ratio is 1. We're assuming the variances are equal. That's good. And I believe that's everything, so let's go ahead and run the test. Okay. Now, the first thing they do is they provide us with a confidence interval that's built in. We asked for a 99% confidence interval, so everything is shown here. Here's the first sample size and the interval for that variance, and here's the one for the second variance. Okay, and there's not much overlap there, but the f-test that we're actually after, the p-value is both on the graph, and it's also going to be right below in the session window. But the p-value is very small, 0.009. Just a little bit less than 1% significance that was being asked. So we would reject the null hypothesis, but just barely. And if we had a slightly larger sample size, we would be able to say a little bit more about the p-value for this problem. But as it stands, the p-value came out. Yes, here's the results we just saw included in the slides. P-value of 0.009. We reject the null hypothesis. Okay, and if we reject the null hypothesis, again, let's refresh our memory. What does that mean in this context? It means we don't think the variances are equal. We adopt the alternative hypothesis that the iron deficiency the iron content rather in elderly gentlemen has less variability than those of younger men. Okay, and let's do one last example. This is kind of a neat one. There's such a thing as called collusion. I don't know if you've heard of it or not. Collusion is what happens when people sort of do backdoor dealings to make the market value of a certain commodity stacked up in their favor so that they come away with more profits. Here's an example of collusion that was reported in a small market. In this case, it was just a tri-county fair where in Kentucky they were taking dairy farmers and they were bidding on supplying milk. So I think that if you're willing to pay this amount for a half pint of milk, then I'd gladly accept that. And the lowest bid, of course, will get the job. But in one of these 13 of these districts, they noticed that a lot of the bids were very close to each other, essentially. There wasn't much variability in these bids. And so right away they suspected foul play, and they went after the milk suppliers, and one of them admitted, yes, okay, we were colluding, we were talking behind the scenes, and we all kind of agreed on a ballpark figure for our bids, and we all placed bids close to that. Who knows? Maybe their deal was that whoever gets the bid, they split the winnings with everybody, so that everybody comes out in favor. But these things can happen. Well, the nice thing is the test that we just developed for variability, we can detect whether or not collusion might have happened, because, as just said, what will happen is all of the bids will come in way too close to one another to be random. Right? If you had a normal bidding process, you might have someone who bids really far over the right price and someone else who bids way too low, but there'd be a lot more variability if people didn't talk about what the right number was ahead of time. So Luckily in Kentucky they have a neighboring area where similar markets were held, and so we have a variant, a sample standard deviation in this case, for the Tri-County Fair, which we suspect of collusion, and just the general surrounding area. So we don't have the actual data, we just have the sample data, but when the full data was available, somebody had made a box plot, and that's included in the slide. As you can see, the surrounding area, as we indicated, a lot more variability and a couple of outliers, people overbidding and someone underbidding on the true value. None of this is present in the Tri-County area that's suspected. So already we have a very good idea that, yeah, I think there was some cheating going on. But if we were to compute an f-test in Minitab, just based on the sample data, go to the same menu we just had open a moment ago, and plug in the corresponding values, you get a p-value of 0, which visually we see it, the p-value confirms it. There's definitely something going on here. There's collusive markets for the Tri-County area back in the 80s when the data was taken. So hopefully it's been fixed. Okay, and that concludes the slides. And so as you begin to look at these problems, please let me know if there's questions with homework, and we can address those accordingly. And I will see you folks next Friday.